Okay, hello everyone. Hello people on YouTube and Zoom. Hello to everyone here in this lecture room on the next Tuesday seminar at the Warsaw University Astronomical Observatory. Today our guest is from Konkoly Observatory. We had guests from Konkoly in last two seminars. So we had a Polish, we had a Turkish, now we have a Hungarian. So Zsofia Nagy is, she's a postdoc in Konkoly, but she traveled around the world. She did her studies in Hungary and Netherlands, and then was a postdoc in Germany and the US, and now is working in Hungary. And Zsofia is involved in the Gaia Alerts program, but from the young stellar objects perspective. So we used to collaborate in previous years, and we're going to hear about some results Zsofia obtained recently with Gaia. Zsofia, floor is yours.
Thank you. And also thank you for giving me this opportunity to present some results here on behalf of my colleagues as well, who are listed here. So it's a teamwork, it's a large collaboration. And I will tell you some results on follow-up observations of Gaia-alerted young eruptive star candidates, not all eruptive. So, oops, okay, yes. So I will start with some introduction on young stellar objects, and then I will tell you about Gaia-alerted sources of different classes of young eruptive or young stars. First, about classical T-Tauri stars. Then I will tell you about one of the main classes of young eruptive stars called EXors, then about the other main class of young eruptive stars called FUors, and then I will show some examples which had Gaia alerts but cannot really be classified into any of the categories. So I will tell you about pre-main sequence stars in this talk, and I will focus on the low mass examples, so stars with masses below 2 solar masses typically. And these are called T-Tauri stars, which are still accreting material from their environment. So the gas and dust fall from the envelope onto the outer disk, and then the material accretes onto the star. And part of this material is removed from the system via outflows and stellar wind. So in this system, one of the main processes is accretion because it heats the disk and it increases the luminosity of the star. And apart from this sketch of how we should imagine such a system, this is an artist's impression, which shows the central star, the disk, and the accretion columns, the accretion streams. So accretion is not so easy, however, because it's not a smooth process. It was thought to be just smoothly decreasing as a function of time as these young stellar objects evolve, but it's not that simple because it turns out to be inhomogeneous in space as well as in time. It can actually vary by orders of magnitudes. It can cause bursts over the lifetime of these young stellar objects. And these bursts are due to the change of the accretion rate because of thermal or gravitational instabilities. But accretion, of course, is not the only method or not the only physical process which is taking place in young stellar objects. So this shows all the timescales and the amplitudes which we can see in young stellar objects. And well, from hours to through days, weeks, months, we can see brightness variations up to centuries. And the main processes are, of course, accretion, which you see with blue. And apart from accretion, many processes are due to change in the circumstellar extinction, which are shown in red. But so typically in classical T-Tauri stars, the processes, the variability is happening on a time scale of, say, days, weeks, a month, but not on, longer time scales. However, those are the sources that I will mostly tell you about. Now I just would like to mention two types where the circumstellar extinction or the change in the circumstellar extinction causes the brightness variations. One such type is UX Orionis-type stars, where the variability of days to weeks is caused by eclipses due to dust clumps in the disk. And then I will actually mention you an example of an AA tau type stars, so-called dippers, where we see periodic or more like quasi-periodic variations, which are caused by eclipses by an inner disk warp. And since I will show you such an example, this is how you can imagine this. So we see the central star, the magnetic field lines, and the disk, a disk with this inner disk warp. And it depends on the inclination, whether we see an eclipse in this case. So for some inclination, we can see this quasi-periodic light variation. For some inclinations, we do not see it at all. But I mean, the whole motivation of this study, apart from having to take it into account that there are many processes going on, what we would really like to see is eruptive young stars. So episodic accretion, where I showed you that the accretion process can cause bursts from time to time. So this is the episodic accretion, which is a very important process in the star formation because it can really help us to understand how it's going on. So there is a problem, basic problem in star formation, the so-called luminosity problem, which means that for young stellar objects, the observed luminosities are lower than those predicted by the models. And if the accretion is episodic, this could be a solution to this problem. So we really need to understand these eruptive young stars to learn about this process. And there are two main types of these sources. So there are those which are called FUors or FU Orionis-type objects, which show long-term outbursts. By long-term, I mean decades to centuries. And then the other type is the Lupi-type stars or EXors, which show short-term outbursts. And by short-term, I mean several months to a year. And there are some other, say, intermediate cases as well. I will show you some examples for those. But first, just a summary of the properties of FUors and EXors, because I will be telling you quite a few of these sources. So the time scale is quite different. Again, for FUors, it's decades to centuries, while for EXors, it's months to years. The burst strength is a bit larger for FUors. In the optical, it's between 4 to 6 magnitudes, while for EXors, it's between 3 to 5 magnitudes. And while we do not see, for obvious reasons, that they are repeated for FUors, for EXors, when we identify such an object, we typically see a new outburst like once every few years. The accretion rates are between 10 to the minus 6 and 10 to the minus 4, typically for FUors, while between 10 to the minus 7 and 10 to the minus 5 for EXors. There is one key difference which can help us identify them, which is their spectra. For FUors, we see typically absorption lines, while for EXors, typically emission lines. So I'm showing an example here. This is the prototype of EXors EX Lupi, showing emission lines spectrum. This is in the K band. And while this is a FUor, which was discovered a while ago, I mean, a few years ago, based on the Gaia alerts, which I will tell you about. And apart from this emission line versus absorption line, there are some other key characteristics of FUors. For example, we see a lot of P Cygni line profiles showing information on the stellar wind. And we see this kind of triangular shape of the continuum in the H band, which is due to water vapor bands. So as I mentioned, based on, apart from these two types, there are some intermediate cases as well. And I'm just showing you two examples of those. So this is PTF14JG, which really looks like an EXor. It's really, a FUor, similar to a FUor. However, its light curve is not really typical. It was more powerful than a FUor, showing an even larger amplitude for the brightening. However, then it didn't really stay in the bright state, but it started fading. And then it shows another little brightening event, and then it continued fading. So it's similar to FUors, but with an atypical light curve and even larger amplitude for the brightening. And then there was another case, again discovered from Gaia Alerts, Gaia17bpi, which shows a timescale for the brightening, which is in between EXors and FUors. So as I mentioned, it's really important to study these sources to understand star formation and episodic accretion. However, we only know about 50 of these eruptive young stars. So it's really important to try to identify new examples. How can we do that? We can use surveys such as the Gaia Alerts System. And so this Gaia Alerts System reports the light curves for sources in one band only, in the G band, which show a sudden brightening or fading. So once there is a light curve for a young stellar object or a candidate young stellar object, we need to confirm whether it's really an eruptive young star or something else. And for this, we need to obtain follow-up photometry and spectroscopy, mostly spectroscopy. But we need photometry because the cadence of these Gaia observations is about 1 data point per month. So if we want to study their short-term behavior, we need higher cadence observations. And spectroscopy is also really key. I will tell you more on the next slide, like how we select these candidates actually. But I just want to highlight the two main types of objects we are looking for. So we are looking for young stellar object candidates, which are brightening, mostly to try to find new EXors and FUors. And then there is also another important question. As I mentioned, for FUors, their bright state or their outburst happens on a time scale of decades to centuries. So we don't really know any example where they started fading, really. So if we really want to understand how these outbursts happen, we need to find some examples where they are fading. We need to measure their physical properties to really understand like how this outburst really happens and how it ends. So the first step, as I mentioned, is the Gaia alert. And then, of course, there are other types of surveys. We can look into different archives to find some more observations like the CTF or PenSTARS or WISE for the infrared. And we can look at near infrared color diagrams as well. And it's important also to check the SEDs to search for infrared, near infrared access. And I also want to mention that in some cases for these sources, even their distance is unknown or it's very uncertain. And in those cases, it's really crucial to study their environment, whether they can be related to a star-forming region, and then try to derive a distance based on the nearby sources. So once we found these interesting sources, which are really good candidates for eruptive YSOs, what we really need for the confirmation is follow-up spectroscopy. So I just want to mention some telescopes which we use for the follow-up observations. For the photometry, mostly we use 1 meter class telescopes. There is one in Piszkéstető, Hungary, and we use the telescope at Mount Sohora a lot. And then when there is a sudden source, we use the South African Astronomical Observatory facility, and we used some other telescopes like the Adıyaman Observatory in Turkey. For the spectroscopy, we used many different instruments. I believe this list is not even complete. I will show you soon some observations from the NOT, TNG, GTC. For sudden sources, we just used the VLT lately. So yes, you will see for the sources I'm about to show you. And just some numbers about, how many sources we are dealing with and so on. Since we started this work a few years ago, we have identified about 50 or more eruptive young star candidates. And we have obtained follow-up spectroscopy for about 15 sources and follow-up photometry for even more. We published a paper on a discovery of a FUor on an AA tau type star and an EXor, and just recently. And we submitted another paper on the variability of two classical T Taurus stars. And there are 5 more papers in preparation. So these papers that I just mentioned are the ones that I will show you some results from in the next slides. So first, I will start with sources which looked like good candidates for eruptive young stars, but turned out to be something else. So this is V555 Ori, which had a Gaia alert in 2017 because it brightened by about 1.5 magnitude. The whole event lasted for like a year or so, this whole brightening event. So it looked like a really good candidate for an EXor type source. Apart from this long-term brightening, I need to mention that when we looked into observations on shorter timescales, like this one from the TESS, we realized that there is a variability also on a shorter timescale, on a timescale of a few days. So when we looked into the details in form of a periodogram, we could find from various data sets, SMART's telescope data and this test light curve, that this period is about 5 days. And as I mentioned in the beginning, this kind of quasi-periodic behavior can happen for AA tau type stars. Now for AA tau type stars, as I mentioned, the variability is caused by changes in the circumstellar extinction because of an inner disk warp causes eclipses in the star. So in the shorter time scale, this is one idea to see actually what's happening on a longer time scale. We investigated the color magnitude diagrams, and first of all, we found that there is no color change at optical wavelength. But so to compare the longer term and shorter term variability, you can see here the magnitude differences at different wavelengths for this 5-day period variation, shown with black, green, and red data points, and the long-term variability, so between the faint state, long-term faint state, and long-term bright state, is shown with blue. And in the near infrared, we can fit these data points with the extinction curve quite nicely and can derive the visual extinctions. And based on that, there is not such a large difference between the extinction change on a longer time scale and the extinction change on a shorter time scale. So these signatures, I mean, these pointed to the conclusion that we really see this circumstellar extinction change, not only on a short time scale, but on a long time scale as well. So the reason why we do not see this, that these data points follow the extinction curves for the optical wavelength is because of scattered light. So at optical wavelengths, these data points are dominated by scattered light. So just to make sure that it really is extinction changes that we see, we obtained the accretion rate from the age alpha line. So we had some spectroscopic data, and from the age alpha line, we obtained the estimate in the faint state and in the bright state. And the accretion rates were found to be quite low in both cases, a few times 10 to the minus 9. So this again confirmed that what we have seen in the analysis of the color differences, we can confirm from the accretion rates as well. So the brightness variations are related to circumstellar extinction changes. And this turned out to be a nice example of an AA tau type star. There were two other sources which we just lately analyzed, which showed a time scale, long-term variability on a time scale of about 1 year, both sources. However, the amplitude for one of them is only about 0.5 magnitude for this Gaia 20bWa. For the other source, it's about 2.5 magnitude. So this means we have two sources with a time scale of brightening, which could point to an EXor nature. However, one of the sources has lower amplitude, but the other source, so Gaia 20 FGX, really looked like it could have been an EXor again, like before. So we obtained some follow-up spectroscopy. We obtained them with the TNG for both sources, and we obtained another spectrum for Gaia 20 FGX. So this is just the lines which we detected. There are different tracers of the accretion rate. For example, the Balmer series lines, bracket gamma, Peshin beta, and there are some lines for Gaia 20 FGX, which were only detected in the second spectrum, which was already during the fading. So the first spectra with the TNG were taken during the bright state. So we use these lines actually to measure the accretion rates during their brightening. And for Gaia 20 FGX, we had another estimate during their fading. And we compared them to other young stellar objects. So these are the accretion luminosities versus the stellar luminosities, and the accretion rates versus the stellar masses. And most of these dots here are from our so they are classical T-Taurus stars. The values were obtained by surveys. And these triangles here are values obtained for EXors. And so this asterisk is for Gaia 20 BWA, and these two are for Gaia 20 FGX. And as we see, there is this general trend, sort of linear trend with some scatter seen for classical T-Taurus stars, while the EXors are definitely above this trend. And our sources are closer to this trend, definitely fit this trend and are not above like EXors. So this proved it to us that even if they show the time scale in their brightening, which was really most typical of EXors and not classical T-Taurus stars, their accretion rates point to the conclusion that they are just classical T-Taurus stars. However, what is interesting is that, as I mentioned, most of the light variability in classical T-Taurus stars occurs in really much lower time scale, shorter time scale, like hours, days, weeks. So these are some of those examples, which would be interesting if we could find more. That would give us some idea that T-Taurus stars can actually have these long-term variability as well, with amplitudes that are actually close to the EXors, but they are still below the EXor variability. So now I will show you some real EXors which we found. So There is Gaia 20 EAE. You can see the light curve here in many different bands. The Gaia light curve is with black values. So this was the brightening event, which was seen, which was shown as a Gaia alert. But once we found all the archival data, we identified another brightening event, which happened years before. So here we have two brightening events on with an amplitude, which is typical of EXors, and the time scale, which is also typical of EXors, and it's repeated, so it was quite promising. We obtained some follow-up spectroscopy with the NOT and the GTC, and we overplotted the spectra, the near-infrared spectra, on those which are from the prototype EX Lupi, and we see quite a nice match between these sources. So this gave us a conclusion that this is a really good candidate for an EXor. I'm saying still a candidate because the accretion rate was measured only in the bright state, and for a confirmation, we need to measure it in the faint state as well, and we have observations scheduled for this. Yeah, you can find more details in our recently published paper by Cruz-Saenz de Miera et al. And there is another EXor type source, which showed a brightening which corresponds to the Gaia alert in 2019. And there were some earlier brightenings as well, not as bright as this event, or not with such a large amplitude, but still. So this was a known young stellar object, and it was found to be in an early evolutionary state among YSOs. And there is an indication of a CO outflow in apex data. So the Gaia alert happened because of a brightening of about with a 4 magnitude amplitude. So we obtained some spectra again with the Gemini IGRINS instrument. And this is one example of the K-band. So there are many lines which were found to be in emission, which is expected from EXors. And there were also some lines identified which can be related to the presence of a jet, like H2 lines. So that is confirming us that indeed it's a young stellar object in an early evolutionary state. So we are still analyzing this source, but again, it's a good candidate for another EXor. I will now show some examples of FUors. So this was the first FUor which our group found based on the Gaia alerts. It's Gaia17bpi. You can see this long-term, so this brightening of the source in the optical and in the wideband in the mid-infrared. This Gaia alerted source increased its brightness by 4 magnitude. To confirm whether it's really a FUor, my colleagues took optical spectrum with the Isaac Newton telescope and the near-infrared spectrum with the NOT. And you can see a comparison of the 18 dBi spectra with other confirmed FUors. And the match was quite nice. So we see all the features that we expect to see in FUors. We see some absorption lines like the CO band had, and some P Cygni profiles, and sort of a triangular shaped H band. So this is confirmed to be a FUor, and this paper was published in 2020, and this source is still in the bright state. So that also confirms that this was a good interpretation. So then I will show you 2 examples which could maybe give us an answer whether or how FUors are fading. So as I mentioned, we haven't really seen any FUor which really faded. And so we are trying to find examples of this. there was a Gaia alert for a source, Gaia 20EGM or V7337, which is a known FUor. It's known since 2007. It showed a slow rise in its brightness between 1971 and 1993, and then it stayed in the bright state. And there was a Gaia alert. So the brightening event had an amplitude of about 4.5 magnitude. So its duration is was about like more than 67 years. So then there was a Gaia alert in 2021 because it started fading. In fact, it started fading fast here. But if we look at this light curve, it has been fading like slowly since about 2015, also seen in the Weiss bands at mid-infrared. So then we observed some spectra to see what might be going on with the Gemini. And indeed, we see some features which can be identified in FUors. Here, the CO band had in absorption. The triangular shaped H band continuum is shown nicely, and many other lines which are typical of FUors in absorption. However, it is still a question whether this fading is due to, a change in the accretion rate or whether it's extinction. I mean, it still could be due to circumstellar extinction. So this is something that we are currently working on. And also, I need to mention that since we obtained this spectra because of the Gaia alert showed this fading, there have been some new data points which actually show some brightening. So yes, we are still trying to figure this out, what's going on with this source. Then there was another interesting source, which we think that might be a fading FUor. But the difference between this one and the previous example is that it's not known in the literature as a FUor. It's only known in the literature as it might be a young star showing a long-term outburst because there was no spectroscopic confirmation of its FUor nature. So this is the long-term light curve by Contreras Peña et al. And I believe some of these really early data points are from photographic plates. So there was a Gaia alert toward the end of 2021. And since then, so it was alerted because there was a fading of about 1.2 magnitude over 18 months. So then we obtained spectra. Actually, we had an earlier spectrum with the Gemini telescope. And then we obtained another spectrum after the Gaia alert with the VLTX shooter. So these spectra again confirm that it's indeed a FUor. So in the H band, we see this triangular shape, and then a nice absorption lines in the CO bands. And there are some other features which are typical of FUors, like we see P Cygni profiles here in this calcium triplet, P Cygni profile again in the H alpha line. There are quite some similarities between the spectrum of Gaia 21 ELV and FU Orionis. Apart from these typical signatures of FUors, we can see some forbidden lines in emission, which point to the existence of a jet. So this is a good example of a FUor, which is fading. However, as you see here, since the Gaia alert, which happened here, there are some data points which show an increase of the brightness. So we still need to investigate like what's going on here, if it's really change in the accretion and whether it's really fading or it will be just a dip in the brightness. So this is still work in progress. Okay, and now I will show you two interesting examples of sources which turned out to be neither FUors nor EXors. So there was this source, Gaia 21bty, which was a young stellar object candidate, and it showed a 3 magnitude brightness increase in 4.5 months. And the brightening was also seen in the WISE data. This is the optical light curve, though. And when it started to brighten, then there was a spectrum obtained, or some spectra obtained, optical spectra by Lynn Hillenbrand. And she published a telegram about the discovery of a new FUor. Here you can see that she compared the spectra of Gaia-20bpi with 2 other confirmed FUors. There were striking resemblances between these spectra, so it really pointed to a FUor origin. However, since then, the source faded back on a time scale of a few months back to almost to its quiescence. So this is really interesting. We still need to investigate what's happening and you know, why it faded, what kind of a source it is, and you know, why we see these similarities between the spectra of FUors. So this is work in progress by my collaborator. And there was another interesting source which cannot be classified into any of the main types of eruptive young stars, which is Gaia 18CJB. Here in its optical spectrum, you can see a really long-term brightening over actually several years. It's still in the bright state. It's a YSO candidate. Its probability of being a YSO is 85%. And we obtained spectra to confirm whether it's really a YSO or an eruptive YSO. The spectrum is still preliminary, so I cannot show it, but it contains emission lines only. We see some tracers of accretion, for instance, the bracket gamma. We see also the CO lines in emission, and there is the presence of H2 lines also in emission, which trace the presence of an outflow. So all these spectroscopic features point to the conclusion that it indeed is a young stellar object. However, we need to figure it out, like which kind, because it's definitely neither a FUor nor an EXor. So, okay, I will summarize in 2 slides. I will just give you a summary, and then I will show you a figure of the sources that I was talking about. So I hope I proved it, that Gaia alerts are really useful to identify young eruptive or just young stars. And it's also crucial to obtain spectroscopic observations to classify these sources. I showed you 3 examples of interesting classical T-Tauri stars, which showed long-term brightening. I showed you the discovery of 2 different EXor candidates, and the discovery of 1 FUor and 2 FUors which might be fading, which would be really, really exciting. And just to summarize this, I showed you this figure in the beginning about all the timescales and amplitudes that we see in the variability of young stellar objects. So the eruptive YSOs, which we identified or classified, observed, there are those of FU Orionis objects, which are here with large amplitudes and a really long time scale, like decades, centuries. We have 3 of them. And then we found and classified 2 EXors, which show an outburst, again, on a yearly time scale, with an amplitude that is not as high as for FUors, but a few magnitudes still. And then there was 1 source where it was circumstellar extinction, which caused the light variability. And it shows 2 timescales for its variability, a long-term one, which showed properties. The brightening showed or looked like an EXor, but then it turned out that it was due to circumstellar extinction. And then it also showed brightness variations on a time scale of a few days. And then I showed you 2 other examples, one of them could really, on this diagram, fall into this range defined by EXors. But when we derived the accretion rate, it turned out that it was just a classical T-Tauri star, which apparently can show this long-term brightening event similar to EXors. And there was another source which showed a lower amplitude, but still a time scale, a variation, a brightness variation on a time scale, which is much longer than the time scale that is typically seen in T-Tauri stars. So, okay, basically that was it. Thank you, and I will take questions.
Thank you very much. Questions, please. Let's start from here. Come forward to the camera. You can sing.
Yes, okay. Can you hear me?
More or less.
Where's the microphone?
In the camera.
Okay. Okay, so thank you for the nice talk. And I have a question regarding this anomalously long EXor. Do you think that this is some new mechanism going on, or is it rather some anomalous, like an anomalous big accretion disk or something like that, or maybe something new which we haven't seen before?
Well, it's a good question. However, we are really in the beginning of the analysis. So to be able to answer this, we need to first calculate the accretion rates and, you know, analyze the data in a lot more depth. It could be like one of those intermediate cases, which I showed in the beginning. There was one case where, you know, the time scale of the light variation was between these two main classes. But, well, we don't know that yet. So I hope next time when I will present this work, I can answer this question. We would like to know this, yes.
Sure. Thank you.
Paweł, please.
Yes, thank you very much for very interesting talk, Zsofia. Well, I thought that we know much more than 50 young eruptive stars. So this was really informative for me. And my question, or rather comments, is that, as you know, we have a network of small and medium-sized telescopes, right? In our ORP collaboration. And a lot of, or some part of your targets, young stellar objects, are already monitored by the network, by the people in professional and amateurs as observers in our network. And the nice example is, for example, Gaia17bpi, because we have gathered a lot of data for this target, and it was used in the paper, so that this is really nice. But for some other, we got one or two epoch data, which is not enough for your research, but probably it is because this target, for example, Gaia 18cJB on the screen,
Right.
This target is not in the black hole TOM or our calibration server, and the people don't know about this target. If we put it in black hole TOM, then it can be scheduled in the observatories on the world. So I guess you can get much more data than presented here. I checked in Gaia Science Alerts webpage, and at the moment we have one data from 50-centimeter telescope on La Palma, except those presented by you on the slide. But yeah, well, this is probably because the people don't know about the target and the alert, that it is interesting enough to be published, and it is important to gather the data. So maybe would be really nice to have some of your stars in black hole TOM in our network to inform the people about the necessity of observing it.
Okay, I think it sounds like a good opportunity, and I believe we could talk about this sometime, like, you know, organize a meeting with my collaborators and discuss like what you would need from us and so on. Yeah, that would be nice. Yeah, at the moment, as you know, many of your targets mimic the microlensing events alerted by Gaia. That's why we classified them based on spectroscopic data, and we rejected young stellar objects from our sample, but the data are very useful for you. So this is good, also good opportunity to continue this cooperation, and not only in spectroscopic, but also in photometric mode. Yes, I agree. It would be quite useful. So I hope we will talk about this soon. Okay, thanks.
Okay, Richard has a question.
Yes. Hi, Zsofia.
Hi.
I have a question related to the interpretation of the variations of some of objects where you invented extinction, influence of the extinction. When I saw the extinction curves with different AV, it means that you had to assume, you had to assume some extinction law. And I think that you assume some typical extinction law, which is dominated by very small grains, which have huge extinction and visual and optical wavelengths. But this behavior clearly shows that extinction and UV and optical is not so high. And this is my feeling, and it would be possible to check that such behavior could be explained by kind of stones. I'm joking. I mean big grains, which do not have significant extinction at these short wavelengths, and then you can explain everything by the extinction. Don't you think so? Am I right that you assume some, I don't know, MRN model or whatever for the extinction law?
Yeah, we assume the typical values. That's correct.
Yeah, so this is typical for interstellar medium. Now we are talking about some physical processes which are going on around star. It's difficult to imagine that the dust formed is similar to the interstellar dust. And it could be quite big. And if grains are big, they do not have significant extinction as it is shown by these lines at UV and optical. So it's possible to make simple models to check if just assuming different dust sizes is possible to explain such behavior.
Okay, I will look into this. Thank you for the
please think to shift just to compute extinction for big grains.
Okay, this is something to consider.
It could give you some idea what kind of grains could form in such environment. Okay, that's it.
Yes, thank you.
Okay, thank you very much. I see another question from Marius, please.
Hello, Zsofia. Thank you very nice for very nice presentation. My question is, so let's say from the practical side, for the detection or prediction with young stellar objects, we use the infrared photometry, and most popular it is the combination between two mass and Weiss, first and second wavelet, and to put this on the color diagrams. And on the position where it is location on this color diagrams, we know that it is maybe first class or second class young stellar objects. But now in your slide, for example, like 26.
Okay, let's see. Yes.
Yes. So here it is on the, no, let's say this points that it is W1 and W2, as I understand, it is WISE.
Yes, that's from WISE, yes.
Yes, that's from WISE. And it is below, it is optical, infrared and optical VB, yes? So here from this diagram, I see that it is the color. It's actually due to this realities changes. Or do you agree with me? Because the distance between WISE and optical or infrared magnitude, it is on this diagram. No, it is changes. So as I understand, so due to this variability, it should be some changes in the color.
Yeah, that's a good question. I didn't look into the colors so much. So in this paper, this is the only paper I talked about in which I'm not, involved. So I'm not familiar with the color diagram. Sorry.
No, okay, because my question actually second question, it is maybe not for you, but it is the question. Can, for example, the star in the color diagram to be in the position like normal star, but in reality, due to this variability, but in reality it is young stellar object, for example, first class. And yes, I understand that maybe it is complicated, little bit question. So no.
So sorry, what exactly is your question?
No. In one of your slides, but I can't remember now this, yes? So typically, if you have two mass color diagram, yes? So young stellar objects typically located on the right side and little bit up. Oh, yes, here. Yes. It is in the, yes. So question, it is very simple. And it's similar color diagrams we can build using two mass combined with WISE data. Color. So here it is about what this objects, for example, like here it is clearly young stellar object due to this variability, because it is the magnitude measurements was made in not simultaneously, but even in a different time. If we combine catalog from two mass and WISE, this star appear in the position like the normal star. So here in this two mass diagram, it will be somewhere close to this left and no, but for example, where it is this black line, it is between 0 and 0.5.
Well, okay,
so actually, yeah, so actually move the star due to variability from the left corner to the closer to the to the left bottom.
Do you mean that using these color diagrams only, we cannot really classify the sources, or?
Yes, can we using this in simplest way? Yes, can we classify the sources using this color diagrams?
Well, I mean, these are not enough, of course. So we use different methods as well, like for example, the SED fitting, or comparing colors as well. But I mean, we do not only use these color column diagrams.
So color diagrams, it is not enough.
I would say so, that it's not, no. We combine information from all kinds of tools.
It's just prediction.
Okay, yes.
Okay, thank you.
Okay, thank you very much. Thank you, Marius. Thank you all for questions. I think we have to stop here. So I thank you, Zsofia, again for your nice talk.
Thank you.
Thank you very much. Thank you all for joining, and see you next week.
Bye.
Bye.